Scientific notation, orders of magnitude, and significant figures. Scientific notation is when we use powers of 10 to simplify very large or very small numbers. And the shorthand notation is in the form a times 10 to the nth power, where a is typically between 1 and 10. There's a few exceptions on that, but it's typically between 1 and 10. And it could be a negative number, that's fine too. And n, the exponent to which we raise 10, is a positive or negative integer. Okay, and when I look at this value, a times 10 to the nth power. So for instance, if I have 9 times 10 squared, right, I'll have 9 times 10 squared, which is 9 times 100, which is 900. And so I took this larger number and I reduced it down to scientific notation. I can do this with numbers less than 1 as well. So let's say I have 9 times 10 to the negative squared power. Well, that's 9 times 10 to the 1 over 100, right? 10 squared is 100, and I do the reciprocal of that, and that becomes 0.09. Okay, so I can take decimals, or I can take large values and reduce them to scientific notation. You can see with these two examples, it may not be necessary, but when we get into really large numbers, for instance, if I wrote this number down, all right, you can see how maybe I'm getting tired of writing zeros out. Or the same if I have a very, 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 very small number as well, right? So that we can reduce these to scientific notation as well. And what we do, and you may notice this here, is the number up here, the exponent, n, in the times 10 to the nth power, is the number of zeros, the number of places between the 9 and where the decimal is. There's 2 here, and you can notice that -2 will be in the -2 direction. Okay, so in this we're going to have a positive, let's see, 3, 6, 9, 12. So this will be 1 times 10 to the 12th power. I have 12 zeros here after the 1, and so I get 10 to the 12th power. Let's see, let's count this. I know I'm going to have 1 times 10 to a negative power. Let me count the zeros here. 3, 6, 9. This will be to the negative 10th power, right? 1, there's 3, 6, 9, 10. All right, that's how far over, how many decimal places I had to go in order to get to the decimal, where the decimal is right here behind the 1, right? So this is to the negative 10th power. So that's how we can do shorthand with scientific notation and large or small numbers, and you will see this over and over and over again and get used to it. And so what we need to talk about is techniques for operations with scientific notation. Okay, and so typical things we can do for numbers is addition or subtraction, right? And so if we want to add or subtract numbers of scientific notation, the easiest thing to do is convert all of them to the same power, and you may be recommended to the lowest power of 10 and proceed. And then also multiplication and division. The technique here is to multiply and divide the first terms, and then multiply or divide the powers of 10 separately. And this is a technique that is expected that you know, and I will show you how to do it in the examples here. So I chose some examples. Scientific notation practice. These are the plus and minuses. And I just want to go through and do some examples here to get used to this. So when I look at these two numbers, notice that both of these have numbers out front. There's like the a term for this one and the a term for that one. I have 10 times 10 to the third and 10 times 10 to the third, right, in both of these. So this is a pretty straightforward addition. And when I look at this, if I want to convert this number, it's 1.5 times 10 to the third, which is actually just 1,520. Yeah, there's 3 decimal places, 1, 2, 3. I move it over. So I'm adding 1520 plus 2510. Those are the two things I'm adding. But the trick for doing this in scientific notation is to add the 1.552 plus a 2.51. And then we're just adding those, and they're both to the power times 10 to the third power. So really all we have to do is add those two front numbers and then tack on the times 10 to the third in here. So I'm going to go ahead and do that. I did this before, and I know the answer, you can plug this through the calculator yourself, is 4.03. These two numbers added up is 4.03, and then it's times 10 to the third. And that makes sense. When I add these two numbers up, I'm going to get 4,030. That's what that says. Okay. So in the next example, notice that we're subtracting, and then we also have different powers of 10 here. And so my suggestion was convert to the same power of 10. Convert to the same power of 10. So, and the lowest one. So the lowest one here is times 10 squared, which means that I'm going to convert this one to times 10 squared. Instead of 10 to the third, I'm going to have 10 squared. How I'm going to do that is go 1.52 times 10 squared. Do you see that? I divided the cubed up into a power of 1 and a power of 2. And I'm going to notice out front here I can multiply these two things together. So this simplifies down to 15.2 times 10 squared minus 7.34 times 10 squared. I'm going to do the same thing I did before up in the prior line. I'm going to go 15.2 minus 7.34, and then I can keep the times 10 squared out back. And when I subtract this, you can do this in your calculator real quick. I get 7.86 times 10 squared. And that'll be the final answer for that question. Notice when I did this problem, and what I mentioned in the prior slide was that you want to convert both of these to the same power. And notice that's what I did. I had a 3 and a 2. I went to the lowest power, which means I converted both of them to the power of 2. And this conversion here happens pretty easily as long as you're accounting for the correct number of powers at 10. I needed 3 total, so I divided it up into the one I was looking for, the square, and then that meant I had 1 left over, and I just multiplied those together in order to get the 15.2. And then I went ahead and proceeded like normal on the previous problem. So let's look at that a little bit more in depth, this sort of changing the power of 10 here. The power of 10, remember out front, this must always be most often, except a few places, a number between 1 and 10. When I add these two terms, I'm going to end up with a number 5 plus 7 is 12 something, right? And so that'll be outside my bounds between 1 and 10, and I'm going to have to do this conversion so that I get the appropriate between 1 and 10. So let's go ahead and do this. I'm going to do this like the first one, 5.032 plus 7.34. They're both times 10 to the 8th, so I can just straightforward add them together. And so you can do this with your calculator. You get 12.372 times 10 to the 8th power. You can see the problem here, 12 is greater than 10, and we want to be between 1 and 10. And so what we're going to do is move the decimal place over, which means that I'm gaining another power of 10 to the first power, right, times 10 to the 8th power, right? This number was 12, now it's 1.2. I gained this power of 10, and what I can do is now combine these two powers of 10. Just like up here, I undid them from 3 to 1 and 2. Here I have 1 and 8, and I'm just going to add those two together, 1.2372 times 10 to the 9th power. And so that's the proper way of adding those two numbers. If you get a number that's greater than 10 or less than 1, you want to convert it so that that first value, that A value in there, is between 1 and 10. Okay, so that's how you do that in that direction and in the other direction. Let's multiply 5.032, that's a familiar number, times 7.34. We're going to multiply those together. And then in this situation, what we're going to do is also multiply times 10 to the 8th power times 10 to the negative 6th power. We're going to multiply those two together. And I guess I don't really need this one here, right? This is the same one, times, okay? So what we're going to do is simplify those powers of 10. Well, we can multiply 5 point something times 7 point something, and you will get 36.93488. You can plug that in your calculator. And then this I'm going to do in my head. 10 to the 8th times 10 to the negative 6. Well, that's 10 to the 8th minus 6, which is actually 10 squared. So I get times 10 squared. So I need to convert the beginning number here. I have 36 point something, and we want to convert that to something between 1 and 10. And so I move it over a decimal that way, which means I'm gaining a power of 10. So overall, this will equal, I'm going to round it off, 3.7 times 10 to the 3rd power. Okay. So I didn't plug the actual terms into the calculator. I just plugged the first terms into the calculator. I did exponential multiplication on the second two terms, and then I was able to easily convert it to some number between 1 and 10. Okay. We're going to keep doing the same thing. Here we're having division. So this is what I'm going to do. I'm going to take 3.6 and divide it by 1.2. We're going to take, those are the A's of those numbers, and then I'm going to multiply by 10 over 4 divided by 10, or 10 to the 4th power, 10 squared. All right. We're going to do each term separately. These are like terms. I'm just combining the like terms. So 3.6 divided by 1.2, well, that's 3. 10 to the 4th divided by 10 squared is 10 squared. 3 times 10 squared. And it's that easy. That's how easy that is. I'm going to do the same trick over here, 1.6 divided by 9.1. And then I'm going to multiply 10 to the negative 19th over 10 to the negative 31st. Same trick here, 1.6 divided by 9.3. 9.1 is, you can do this in your calculator, 1.758. Okay. What I'm actually going to do up here is negative 19 plus 31, right? 4 over 2, right? 4 minus 2, that was easy to get to. So we have to do negative 19 minus a negative 31, which is negative 19 plus 31, and gives us 10 to the positive 12th value. Well, notice again, we're violating between the 1 to 0 rule, or 1 to 10 rule. So let's move this 1 over, so that'll give us 1.758. We've lost a power of 10, so that means I'm going to go 10 to the 11th power. I reduced that 12 because I moved the decimal point in the negative direction. I'm going to lose a power of 10. So that's the answer on that one. And similarly here, 14.90 divided by 11.175 times 10 to the negative 1st over 10 to the 4th. We're going to do each one of these terms separately. You divide this out and you get 1.333. Conveniently, it's all 3's. And then notice I have to the negative 1st and to the negative 4th. When I bring it up, bring the reciprocal, so I get 10 to the negative 5th power. And that's how you do scientific notation, math with scientific notation, the shorthand. You can plug it into your calculator, but notice in a lot of these situations, it was a lot easier for me to just do the math in my head on the paper, or just write these numbers down rather than take the effort to plug it into my calculator. And you'll find that as we move along. Powers of 10 in orders of magnitude. So you're seeing that we have this scientific notation. And what it allows us to do is have exponential notation with these factors of 10. And some of these factors of 10 are more frequently encountered than others. Notice in science we have a vast array. Okay, we have a great range. And I have an example for you that exemplifies this. But metric prefixes give us this shorthand for, if I have let's say the size of a nucleus is like this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, which is 5.29 angstroms. I'm pretty sure that's the right number. Or I can just say that, angstroms, right? So this is, when I wrote it out, I was going to 5.29 times 10 to the negative 10th power. But the shorthand with metric, and we can do this with many other ones, right, is that we just assign it a special prefix. There's a special prefix. So you may be used to, we can go from meters to kilometers, right, where 1,000 meters is 1 kilometer, and that's what kilo means, right, is 1,000 kilometer. So we have this range of prefixes, and these are typically in the appendix or in the front of physics textbooks, often many textbooks in the chapters, and you'll be able to quickly find these and you're expected to know how to use them. So here's the practice I chose for us. Put the following distances in order from least to greatest. And you're looking down here at the sun distance. These are all in meters, except look at this one. This is in nanometers. And some of these are just listed with commas, and some of them have, this one has scientific notation that has a different, remember, diameter of the hydrogen atom? So that's what that number was. This is in scientific notation. So this is what we're going to do to make this the easiest thing in order to compare all of these numbers, right? Because we need to get from least to greatest. We can kind of guess these, right? Let's see, this is pretty small. This is pretty small. So these two are the two smallest ones, right? We can kind of guess. But what we're going to do is just put all of them in scientific notation. Shoot, why not, right? If all of them are in scientific notation, we can look at the times 10 to the whatever power and know the largest numbers are going to have the largest power of 10 there, and the smaller numbers are going to have the smaller power of 10 there. So I'm going to go ahead and put these in scientific notation. So I know what to do. I'm going to put a decimal place after the first digit that's significant. So I get 1.496. And then I'm going to go times 10 to the, no, let's count the decimal places that we need to go over. 3, 6, 9, 10, 11. Did you catch that? 3, 6, 9, 10, 11. 10 to the 11th power. Okay. So I convert that to scientific notation. This you may already know because it was the example in the previous slide. Let's do this. Double check. 3, 6, 9, 12, negative 12. All right, so there's that. Diameter of the hydrogen atom, 3, 6, 9, 12. There we go. Okay, this one's already in scientific notation, times 10 to the 8th. Let's see, 0.6. Let's do this. We need to convert twice, don't we? Because this is 0.6 times 10 to the negative 9th. Nano is 10 to the negative 9th meters. But I want to put the 6 out front, right? And then have times 10 to a power. I had to move over 1 in that direction, which means I gain a negative. So a negative 9 plus a negative 1 is a negative 10 power. Okay. So we're getting our numbers and our powers here. This is 1.0911 times 10 to the 4th power. I had to move the decimal place 4 places. And this is the speed of light, how far light travels in 1 second. 2.997. Let's just start there. 2.998 times 10 to the, how many times do we have to shift it over? 3, 6, 8. So when I'm looking at this, we have a little bit of a tie going on here. Here's the 10 to the 8th power, and here's 10 to the 8th power. This one's the smallest, so B is the smallest, 10 to the negative 12th. D is the next smallest, 10 to the negative 10th. So I'll cross those out that we've used them. Oh, what's the next one? 10 to the 4th power? Yeah, 10 to the 4th power. So we get E, use that one. Then it looks like the largest one is definitely A, and I have to place the other two based on this power of 8. Which one's larger, 6.9 or 2.998? So it looks like this is the second largest, and this is the third largest. So I'll put an F there, and then the other one is C. And that's how scientific notation makes it easy for us to compare the orders of magnitude. Do you see that? How many orders of magnitude? And that's how we would say that. Between these two, how many orders of magnitude? 10 to the 11th divided by 10 to the negative 12th. Well, there's 10 to the 23rd orders of magnitude between those two numbers. And it is, right? One's really, really large, Earth to Sun distance, as opposed to the diameter of a hydrogen atom, right? The Earth to Sun distance is 1 times 10 to the 23rd power times larger than the diameter of the hydrogen atom. That's what that means. So comparing magnitudes, values, getting an idea of the range of scale, right? This magnitude. So last thing I wanted to talk about in this was precision and scientific significant figures. Okay, precision of a measuring tool is related to the size of its measuring increments, and thus to an associated uncertainty. If I have a ruler, there's little marks on it, and I can only be sure that it's past this mark and before that one, unless there's another mark in there. And so the precision of a tool is limited, whether it be the simple idea of a ruler or other ways that we measure, microscopes, etc., right? And so there's what we talk about is the significant figures, or how well that number was measured, expresses the precision of the measuring tool. The smaller the measurement increment, the more precise the tool, and the more significant those numbers are that I'm able to write down that I actually know from my measurement, becomes the significant numbers becomes larger because my precision is more accurate, right? So to determine the number of sig figs, this is what we reduce, right? It's shorthand, sig figs. We count the number of digits in a number, okay? Zeros are significant unless they're used as placekeepers, and I used this term before, placekeepers. So when I think about a placekeeper, 1,000, there's 3 placekeeper zeros in here because it needs to hold the 1 over, right? In theory, I just have 1 times 10 to the 3rd, right? And I really just know one number with really good precision. I don't know these other numbers. As opposed to another situation where there's point holders would be a situation like this. Those are placekeepers as well. Okay, they're just making sure that the 3, you can see that the 3 is over in the 10,000th place, and it holds that distance over there. Again, we'd end up with, this is actually 3 times 10 to the negative 4th power, right? And there's still 1 digit out front that we really know. Okay, so when I look at these down here, to avoid ambiguity with significant ending zeros, write in scientific notation. So that was what my example was. Write these in scientific notation, and that allows you to see the significant figures better. So when I just have some examples down here, what are the number of sig figs? And I'm going to rewrite this into scientific notation. I know this is 1.3 times 10 to the 3rd power. When I look at these zeros are just placeholders. They don't have, I'm not sure what they are, all right? So in this situation, there's only 2 sig figs here, 1 and 3. You can see just like the 0.003 over here, we have, this will be 4 times 10 to the negative 4th, and so there's only 1 sig fig in this situation, the 4. Okay. In this situation, 51.32 0.80. Very interesting, right? We have this 0 out here behind everything. And when I look at this, because it's behind the decimal place, there's no reason to have that 0 out there unless you specifically measured it. And that's what I'm going to note in this situation, is that that 0 is there because it is significant. It's not holding the decimal anywhere. I could leave that 0 off and have the same equivalent number. If I left a 0 out in this term or in this term, that's not the same case, right? But for this one, it's the same number. So when I count the number of significant figures in here, all of them are significant to me. So I have 2 and 4, and so there's 6 significant figures in this situation. All right. And I know that's what's going to be a little bit iffy. Okay. So this is just practice. We can practice a little bit more. In this situation, we can kind of already see, right, scientific notation. There's no zeros here, it's just the 4.5, and we can just say that there's 2 significant figures here. This is the situation where the 0 is not a placeholder as well. Just like in this situation, also here, the 0 is in between. I need that 0 there. It's part of the number. The 5 is also in there and was measured from what I can tell. So in this situation, I'm going to have 3 significant figures. Significant figures are a little weird, but what we will need to identify, and it will usually be clear, you'll be able to count the number of decimal places, and that will be, you'll be able to figure out the number of sig figs easily. Once you've figured them out, we're going to do calculations, right? It's just not the actual finding of the sig figs, but we're going to do things with numbers and know those sig figs as well. So identify the number of least precision. When you look at a problem statement, there's going to be a number of least precision. And you might have numbers that have like 4 sig figs and 3 sig figs and 2 sig figs, so you isolate it down to the 2 sig fig one because it's the lowest, the least precision, right? There's only 2 significant figures there. Once you identify that, with subtraction or addition, you can have no more decimal places than that least precise measurement. So I have examples of this on the next slide, and I'm going to hold off giving examples. But we're going to keep in mind this has to do with decimal places and how many decimal places the digit is known to. As opposed to multiplication and division, the result should have the same number of significant figures as the quantity having the least number of significant figures. So this deals with decimal places, and this deals with the significant figures, the actual number of significant figures. So for the most part, I'm not too worried about significant figures in general. I'm not going to assess specifically on them. It will do well for you for online homework or etc. where online entry will specify typically how many decimal places to enter. And I recommend keeping 3 to 4 sig figs and intermediate calculations so that you can maintain your accuracy for an error of margin in the online entry homeworks. Okay, so let's do a few examples here, and that'll close us up. Calculate the numerical answer with correct significant figures. So you can see the first example is addition and subtraction. The second example is multiplication and division. So when I look through here, I'm going to notice that there's 4 decimal places here, 1 decimal place here, and 3 decimal places here. And so I'm going to identify this as being the least accurate measurement for addition subtraction because it has only 1 decimal place. The other one has 4 and 3. This one only has 1. So when I add up, I'm going to round to 1 decimal place. Okay, that's our least precise number, and when we're adding and subtraction, we go by decimal places. So when I add these up, and you can notice 1.5 minus 0.9 is 0.6, and then I add it on there, and you may be able to guess that, and you can run this through your calculator, that we're going to get 644.69 0.923. Is that correct? Let me do this. It seems a little large. 642.3 plus 1.506 minus 0.8863. Yeah, that's what I thought. And you can run this through your calculator. I get 642.9197. Okay, so 4 decimal places. But we're noticing that this has 1 decimal place. The least precise number has 1 decimal place, so I'm going to round it to 1 decimal place. So this will be 642.9. 1 is not larger than 5, and so I will round the I don't have to round up here. I can just keep it like that. Okay, so there's addition and subtraction with sig figs. Multiplication and division, what we're going to do is we're going to count our number of significant figures. What I'm going to note in this situation, this has 4 significant figures. This has 4 significant figures. And also this has 4 significant figures. They had different numbers of decimal places, but they have the same number of significant figures. So when I process this through, when I run it through the calculator, I'm going to get a value. And what I got was 1091.3954664. You can do it for yourself. You can run through and get that number, right? But really, I only want 4 significant figures. So when I look at that, that means that I need to cut it off here. Do I have to round? Is 3 greater than 5? No, so I'm left with 1091 with 4 significant figures. You could leave it like that. You can convert it to scientific notation, 1.091 times 10 to the 3rd power. I don't think it buys you anything. This is just as easy to write as this, if not easier. So that would be the answer. And how you do significant figures in operations.